Welcome to the second and final part of Unit 12. In this part, we are going to be doing two examples involving momentum and impulse. The first example is fairly straightforward. We have a 2 kilogram object moving at 3 meters per second to the right. So, two questions. What is this object's momentum, and would the momentum be the same if it's moving in the opposite direction? So for part one, as always, I like pictures. So here we go. Pretend I can draw a flat line. So the momentum is going to be 2 kilograms times 3 meters per second, which equals 6 kilograms meters per second. Now notice the little arrow. It's a reminder that this thing's a vector. So the direction would be, as I've drawn it here, to the right. If I had the object moving at 3 meters per second to the left, then the momentum would still have a magnitude of 6 kilograms meters per second. But the direction changes. So the momentum is not the same because of that change in direction. The next example involves a ball hitting a wall. And I give you all sorts of specifications: the mass of the ball, how quickly it's moving before it strikes the wall, the amount of time at the collision. And I asked two questions. One is based on the ball rebounding, and the other one's based on the ball sticking. So let's begin with part A. In part A, our initial situation looks like we have the ball traveling at 25 meters per second towards the wall, and then the final, or after the collision, it is rebounding at 25 meters per second away from the wall. So now I can let the initial momentum be the mass of the ball times the initial velocity of the ball. Because everything here is a vector, I have to worry about direction, so I'm going to let positive be to the right in this case. So this is 0.06 kilograms times 25 meters per second, which works out to be 1.5 kilogram meters per second, and it's positive because it is to the right. Our final momentum will be 0.06 kilograms times a negative 25 meters per second, because the ball is now moving to the left. So the final momentum will be negative 1.5 kilogram meters per second. And I can find the change in momentum by taking the final momentum, subtracting the initial momentum, which is going to give me negative 3 kilogram meters per second. I can now use the other definition of impulse. So remember, impulse is net force times a time, which equals a change in momentum. And find the force on the ball by taking the change in momentum and dividing by the time interval. So that's negative 3 kilogram meters per second. The time interval was given as 1 millisecond, or 1 times 10 to the minus 3 seconds. And when you divide that out, you get negative 3,000 newtons. That is part A. Part B starts the same. So the initial looks like we have a ball moving at 25 meters per second towards the wall. But the ball here sticks to the wall and is not moving afterwards. Our initial momentum is the same as what we found in the previous slide because the setup was the same. Nothing changed, same numbers and everything. Our final momentum for this one is going to be 0 kilogram meters per second. And that means that my change in momentum will be negative 1.5 kilogram meters per second. I can now use that the net force multiplied by time equals the change in momentum to find that the net force on the ball is the change in momentum divided by the change in time, which is negative 1.5 kilogram meters per second divided by 1 millisecond. And that gives me negative 1,500 kilograms. Oop, wrong units. Let's try again. Negative 1,500 newtons. So now take a minute and think about this. It takes more force in order for something to rebound, to bounce essentially, than it does to get something to stop. Okay, a good way to think about this is in terms of acceleration. In order to stop something, I have to take away the velocity that it had to begin with. In order for something to rebound, I have to take away that velocity it had to begin with, and then I have to increase the velocity in the other direction. Therefore, the acceleration is going to be larger in the second case, leading to a larger net force. This concludes the 2 examples for this part. In our next unit, we are going to be looking at the concept of conservation of momentum.